Okay, so that's a pleasure to be here, to meet many people that I know, and to give this doctoral course at Institut Fourier. It's my second time in Grenoble, and I really enjoyed the city and the place with all the mountains and so it's so beautiful that, well, why not come as often as possible? And okay, so I had a very quick discussion with Claude Viterbo just 2 minutes ago, who told me that probably I will do some things that he has done already, but sometimes it's better to look or to understand things twice than to not understanding anything. So, but it will be probably a bit different. Okay, so also I'm very sorry that I was unable to speak yesterday. I was sick. And so now, hopefully, it will be better. Okay, so let me go relatively quickly. So there is no break, huh? It's 1 hour and a half, non-stop. Non-stop. Okay, great, wonderful. I like this. I like this idea. Okay, so let me probably go relatively quickly. So okay, so what I want to do is the following. So in the first course, I want to do the preliminaries. So about symplectic manifolds, Lagrangian submanifolds, the Moser argument, the applications of Moser argument to generating functions, and then maybe just a bit of integral systems, and then the notions of geomorphic curves, and some results about that. And so that's the first course, more or less, which is the preparatory material for tomorrow. Is it tomorrow? My second talk is tomorrow? Okay. So, thanks. And then in this second talk, what I would like to do is to describe what is quantum homology and Floer homology. So both are isomorphic, but actually it's quite a very interesting result, the fact that they are isomorphic, because they are completely different. I mean, Floer homology comes from the idea from Floer. So Floer homology comes, of course, from Floer's work, whose idea was to detect and somehow classify periodic orbits of Hamiltonian flows. So Poincaré said very clearly that if you have a non-integrable system in Hamiltonian dynamics, if you have something which is not integrable, then it is completely crazy what happens in this system. It's extremely hard to understand what is really happening. And so Poincaré had decided that one way to have a kind of grasp on the knowledge of Hamiltonian systems in general would be to start from the periodic orbits, and then somehow to relate one to the other in some clever way. And this program was only realized by Floer in the 80s, just after the work of Gromov. And so the Floer homology is all about that, all about this idea that we should try to understand the periodic orbits of Hamiltonian systems, and then to connect each of them together to find somehow the homology to relate that to the homology of the ambient symplectic manifold. So this is Floer homology, and quantum homology is something completely different. It comes from physics. Actually, it comes from the work of Witten, who wanted to understand sigma models, and which are really, very simply a very simple object in mathematics. So when he was working on quantum homology, on these sigma models, he realized that there was a kind of new product on the ordinary homology of a manifold. And this new product was exactly the Floer product in Floer homology. So the fact that these two homologies are the same is absolutely not trivial at all, because they come from two different sides of mathematics. Actually, one comes from mathematics and classical mathematics, Floer homology. It's all about periodic orbit of classical systems, whereas the other one, the quantum homology, comes from quantum physics and has nothing to do with the first one. And they were discovered at the same time, that is, during the same decade. Okay, so I thought that I would give my lecture. Oh, so this would be the second lecture And then the third one will be about the application of quantum homology to the structure to a conjecture that I made a few years ago with Douza McDuff, which is a conjecture about the splitting of homology of Hamiltonian fibrations. So that is fibrations over any base, not necessarily symplectic, so over any base whose fiber is a symplectic manifold, and whose structure group is a group of Hamiltonian diffeomorphism. So in this case, the conjecture is that the homology, the rational homology, not necessarily the integral, but the rational homology of the total space splits as a product, a tensor product of the homology of the fiber and the homology of the base. So this is the third course, and then the fourth one would be about applications of not quantum homology, but cluster homology, or let's say Fleur homology. It will be so the first lecture will be actually about the relative version of the third lecture. It will be a relative version of the third lecture, and I think I would simply explain that when I will be at that lecture. Okay, perfect. So. So, do you have questions or comments, or would you like to change that plan, to add something or to subtract something? Okay, perfect. You are very quiet. What a nice audience. Okay, so what is the symplectic manifold? So I thought that I would give my lecture in both languages, in French and in English. So I thought that I would speak in English and write in French, or maybe the converse. But I think that I was convinced that it's better to do everything in English. Okay, so yes, it's better. Yes, okay. It's better to do. Is it better to do everything in English? Yeah. Okay. Perfect. Okay. So everybody understands English. Okay. Great. Wonderful. Okay. So then, what is a symplectic manifold? So so M omega. So M is the manifold of dimension of even dimension, and omega here is a closed non-degenerate two-form. So this is a symplectic manifold, and then a symplectic submanifold W inside M is simply a submanifold. It will be of even dimension, actually. It is forced to be of even dimension. So it is a submanifold such that the restriction of omega to W is non-degenerate. Okay, so now Lagrangian submanifold. Let's say L for Lagrange inside M is a submanifold. So it's a submanifold such that omega restricted to L vanishes identically. So this means that so when I write this, it means that the pullback. So to be precise, because there are two ways to understand this. If L is here, and then this is M, to say that it is Lagrangian means that on each tangent space, at each point, on each tangent space, we want omega to vanish on that tangent space. We don't require that it vanishes on the whole ambient tangent space to that point. Okay, so this, to be precise, this means that if iota is the map from L to M, just the inclusion, then we mean that iota star of omega is equal to 0. Okay, so it just needs to vanish on that subspace. Okay, so now what is the symplectic diffeomorphism? So of course, this is the usual notion that you know. So simp of M, omega, is simply the group of, so this is the group of all f from M to F, M to itself, such that f star of omega is equal to omega. So it's simply the usual group. So this is, let's say, infinity. So the smooth diffeomorphism of M to itself inside to itself that pulls back omega to omega, that is, it preserves omega. And then the Hamiltonian group of M omega is by definition, so it's by definition it's a subgroup of simp, actually of simp 0 of M omega. By 0 here I mean the identity component of the group of symplectic diffeomorphism inside this. So this is included here. 0 of M called the identity component. Identity component. Okay, now ham is defined. So ham is a bit more difficult to define. It's not as obvious as this one. So it is defined as a subgroup of the identity component of the group of all symplectic diffeomorphisms of M, such that so this is the set of all time one map. Time one maps. Time one maps of flows phi t and 0, 1. So the fact here that I choose 0, 1 as the parameter, as the space of parameters for phi is simply a convention. It could, if you change this convention from 0 to 0, 0, 1, if you change it from 0, 1 to 0, a, it will not change the definition of ham. So we can perfectly take just simply this. And so this is the time one flows of phi t that are generated. Okay, so that are generated by a vector field x. So a vector, so it's a priori a time dependent. Okay, of course it could be time independent, but okay, time dependent. A time dependent vector field. A time vector field x t, which is the symplectic dual. Yes, I would always use S dot to say symplectic. So the symplectic dual of a function of dHt, where ht is a family of function from m times 0, 1 to r. Okay, so this is the definition of ham. So I think that probably you have seen this with Claude. It's possible. Okay. I think I hope you don't mind if I repeat a few things that was done before. Okay, so in any case, so this is the definition of ham, and so what do I want to? So yes, I wanted to maybe to talk about the Liouville-Arnold theorem. So Liouville. So the Liouville-Arnold theorem. So let's say that so a system is a system H from m omega to so let's say to n to r is completely integrable. It makes a lot of noise, isn't it? Okay, it's completely integrable if there exists n minus 1 other functions h2 hn from m to r that verifies the following conditions. In one, there exists a dense subset. There is some subset of regular values. Regular values of h which is by definition just the tuple h1 up to hn to Rn, such that dh1 up to dhn are linearly independent. And 2, maybe I should just get a bit higher. Okay, 2 h1 up to hn are in evolution. Which means that by definition, involution means that the Poisson bracket of each one with any other is 0. So this means geometrically, this simply means that if you take the flow of any of, let's say, of hi, and then you, so for some time, and then for some other time you take the flow of hj, then you get to a point, and this point is the same as you do as if you do the same but with the reverse order. You go from the same point by the flow of hj, and then for given the given amount of time, and then using the flow of hi. So this is exactly what this means. Okay, so geometrically it's very simple. So this is the second condition, and then 3. There is, of course, the condition 3 is obvious somehow. It's just a non-triviality condition. So there exists at least a regular value. So there exists a regular value of h from m to r n. Okay, such that which is not non-trivial. So non-trivial means that h minus 1 of c, so regular value c, let's say. So non-trivial means that h minus 1 of c is not empty. Okay, so this. Okay, so these are. Yes. Okay. So yes, plus the fact that. Sorry, plus the fact that that the preimage here of C is closed. Okay, we don't want to have something which is open, like an annulus, for example. Yes, sure. I'm sorry. This is the Poisson bracket, exactly. Yeah. Sorry. Yes. So this can be defined. Okay, so this is defined in the following way. You take dhi applied to xhj. That's the definition of this. Okay, that's one definition. And in the context of this course, this is the best definition. Okay, and this is anti-symmetric. Okay? This is anti-symmetric. Yes? No, I have not finished. No, yes, I have not finished. So this is so a system is called completely integrable if there exists n minus 1 other functions. Okay, so it means that together with h1 we have n functions which are in evolution and that satisfy these conditions. Okay, but now the theorem comes. Okay, this is just the definition. Maybe stop. So okay, now the theorem is the following one. Okay, so in this case, h minus 1 of C is a torus of dimension n. Okay, so that's S1 times S1 n times. and there exists a DFO. So there exists a DFO from Tn to itself. Let's call it phi, or psi, such that which maps the flow. So this of course, because this is in the inversion measure of C, this torus is invariant under the action of the flow and of H. So this is invariant under the flow of H1. Okay, and then this there is a DFO that sends this, so the torus to itself, such that the psi of the flow becomes linear. So it's just a linear flow on Tn, which by definition is simply the fact that it's generated by a vector field of a form x of θ1 to θn is equal simply to A1 del θ1 up to An del to del θn. Okay, so this means that if you have a completely integrable system, you can always linearize. So first of all, you can always restrict yourself to a subtorus of the torus, which is a submanifold of the symplectic manifold M. If M is if the preimage is compact, because if the preimage is not compact, then actually this theorem is false, because instead of Tn you could have, for example, annuli. So actually anything that resembles in some sense Tn, so which for example is an annuli or the product of a torus with an annuli and so on. But if it is compact, it has to be Tn, and then this flow is always linear. So meaning that it is linear does not mean that it closes up after some time, because it could be irrational, of course. But at least it means that it is linear. Yeah, sure.
H is linear.
I'm sorry?
You mean the flow of H is linear?
The flow of?
H is linear. Which flow?
Yes, I said that this is so Tn. So Tn is invariant under the flow of H1. Okay, so the flow of, maybe H1. Okay, perfect. So, okay, now if, of course, if H is autonomous, so what does it mean? So definition, say, H is autonomous if so H as a function of M times 0, 1 to R is autonomous if it doesn't depend on time. Okay, so if it does not depend on time. Okay, so now of course if H is autonomous, and let's say that it is generic. So generic means that it is Morse. So if H is autonomous and Morse, then it implies, of course, that there exists at least summation of Betti number of M, let's say R. So E goes from 0 to N, fixed points of H of phi of H, phi 1 of H. Okay, so phi 1 of H, so you take H, you integrate the flow of H. So you as usual, you take H, you associate first the. I'm not sure that I've said that correctly, but probably Claude did that correctly. So you take H, you associate to H a differential of H, and then you take, and then so this is the intrinsic, of course, and then you take the symplectic form to pair this with omega, so exactly like a scalar product, you get a flow xh. Okay, I should have said that at the beginning, I think. So this is the way you assign to any Hamiltonian function a diffeomorphism. So you take this, and then you get a vector field, and then this vector field, you integrate that over time. So if H is autonomous, then this is exactly what you do. If H is not autonomous, that is if it depends on time, you do exactly the same thing. Okay, so you get a vector field that depends on time, but then of course you can integrate it. And you get also at time 1, you get, so this is the time 1, I mean, okay, so here I take the time, I put the time there. So, so you get, of course, obviously, you get this number of fixed points because this is a number that is a lower bound for any Morse function on H. So it means that these points here are fixed in the sense, in the trivial sense, that is, they don't move at all. Okay, but what could happen, and what will happen, is that you could have also, so you could have in the motion of, so if you take phi 1, so if you look at phi t of H, you could, so if you look at phi t, so you look at the manifold M, you take a point P, and so these are the points that are fixed all time for all this time from 0 to 1, and then but you could have other points Q that moves along during the time, and then that close up at time 1. So this lower bound is completely obvious, but we could of course expect more fixed points of the flow phi 1. Okay, of the diffeomorphism phi 1. Okay, and this is exactly the idea of the Arnold conjecture, which is now proved in full generality. So Arnold conjecture now, which is it is still called Arnold conjecture, but right now I say it's a theorem. So it was first proved for special manifolds M, but now it's proved for all manifolds M, all symplectic manifolds. So it simply says that if even this lower bound for the number of fixed points is still the same, even if the flow is not autonomous. So this lower bound. So even if the flow is not non-autonomous. Okay, so this conjecture has a long history. It was stated in the 60s, and it was proved by Fleur in special cases in the 80s, and in full generality in the years 2000 something. So the idea is the fact that, so the proof of this is completely, so it has been, so all proof of that, whatever the conditions are on M, are based on the initial idea of Fleur to use Fleur homology. And so Fleur homology is exactly the homology that relates all these periodic orbits. So if phi t is given, so phi from 0 to 1, from some ht. So if phi t is given, then you take as generator of your homology all the contractible loops, in M, inside M, starting at some point and going back to that same point. And then you connect them by, you use that as generators of your homology, and then you construct some differential related to that I will explain later, not today. And you construct some homology about starting from this, and you show that Fleur showed that this homology is actually the same, at least as a not a ring, but as a group or vector space over R. It's the same as the ordinary homology of M. Okay, so if it is, so once you have proved that, of course, it means that you have many periodic orbits. Note that it's very important to know that, of course, this is not obvious because in general, it is not the sum. Okay, you have to understand that this is very specific to the fixed points of symplectic. I mean, from very specific to fixed points of Hamiltonian diffeomorphism, because in general, if you take a diffeomorphism of M with itself onto itself. So then you take the identity here. This is the identity. So this is the diagonal. So this is a graph of the identity. And then it's well known. I mean, this is elementary. You know that if you look at the graph, of an arbitrary diffeomorphism from M to itself, then the number of points that you get here, so these are exactly the fixed points. So the number of fixed points that you get in general is bounded from below by the alternated sum of the Betti numbers. Not the sum, okay, but the alternated sum. Okay, so in general this is larger or equal to the sum of 1 minus 1 to the I of the beta up of this. Okay. And actually, in general, because this is simply the Euler characteristic of you just look at the because this can be just seen in the cotangent space of that symplectic submanifold. So in general, actually, even if M is not symplectic, so you look at the diagonal and then any diffeomorphism, which is C1 close to the identity or C0 close to the identity, can be seen like this as a graph, and the number of fixed points is given by a Euler characteristic, which is exactly this. So this is what we expect in general, and the theorem, the theorem so the conjecture, which is now a theorem, is that what you get is much more than that. Where did I? Yeah. So it's much more than that. It's not the alternate sum, but it's the sum. Okay. So. So what is the idea if the other one doesn't move?
I don't know.
It's not useful. No, I know we have the same thing in Montreal. I'm the director of an institute where we have exactly the same kind of blackboards. There is one that doesn't move and the other one that moves. No one says, no one understands all. Okay, so okay, so this leads me to next talk when I will talk about quantum homology. Actually, I'm not sure that I will have time to talk about Floer homology, but I will certainly talk about quantum homology. And I will probably take enough time to give an idea of the isomorphism between both. And then, as I said, in the third talk, in the fourth talk, I will talk about applications of quantum homology or Floer homology to topological properties of symplectic manifolds. And I've not said that, but in the fourth talk, I will explain why, if you have an isotopy of Lagrange submanifold that come back to itself in a weakly exact manifold, I will explain that in the fourth talk, why this always induces the identity. So this is based on the applications of quantum homology to a kind of generalized quantum homology. It's a kind of relative quantum homology to these systems. Okay, so now, I'm sorry if maybe I will probably overlap with Claude's talk, but I really need to be sure that you understand the following thing. So I'm sorry if you are going to hear that for the second time. I just wish that you forgive me, and because it's very important actually to understand what I'm going to say. So it's about linear algebra. So linear algebra on the symplectic spaces. So now you just take beta, which is a bilinear form. On some real vector space that I will call the V. Maybe let's say of dimension m. Okay, for the moment m is not necessarily even; it's any number. And then the first observation is that there exists a base or a basis. I think it's a basis. Is it a base or a basis? I don't remember. Okay. So I think so. There is a basis. I think it's a basis. There is a basis V1 to Vm. Oops, I don't want this to be n. Sorry, n, such that beta of V2I minus 1 Vi V2I is equal to 1 for all I on m up to n, and beta of all other objects is equal to 0 otherwise. Okay, perfect. So that's a very elementary lemma, if you check. It's a lemma, and then which is an exercise. And then so beta is non-degenerate if and only if n is equal to, so m is equal to 2n. So now the definition is the following. W inside V. So now everything is a vector space in this linear algebra part of the talk. So V is this real vector space, and W is a real subspace, real vector subspace. And so this is symplectic. Symplectic, if by definition, this is a definition. So if beta restricted to W is non-degenerate, so here once again when I say beta restricted to W, I mean of course iota star of omega of beta non-degenerate, where iota is just the inclusion of W inside V. Okay, so that's the first thing, and now the second thing is to say what is an isotropic subspace. Okay, so W inside V is isotropic. Okay, if what did I say? Okay, perfect. Yes, if beta restricted to the tangent space of W is 0. Now W is Lagrangian. Maybe I should say coisotropic. Just I will not need coisotropic, but isotropic, just for the sake of completeness, if omega orthogonal is included in omega. So this is the orthogonal for of course for beta. Okay, so these are the beta orthogonal vectors of for W, and then finally W is Lagrangian if it is isotropic and of the highest possible dimension, which is the half of dimension of Vm. Okay, so now yes, so now in this definition I would like to have maybe now yes I need to say that Vm is beta is non-degenerate on Vm. So yes, so assume that assume that m is equal to 2n. Okay, so I have to assume that V is now a symplectic space. Now, in this case, the top dimension for which a subspace can be isotropic is the half of the dimension. So so this is 2n. So if dimension of W is equal to 1/2 of dimension of V, and is isotropic. Okay, perfect. So that's. Okay, just now a few lemmas which are very easy as an exercise. It's bizarre because sometimes these elementary lemmas of linear algebra are simply the most difficult thing to understand. So it's a good thing actually to go through these lemmas. So now the lemmas are the following. So I have a series of lemmas. I will not show, to demonstrate them, but it's enough to just to state them, and then you can prove it. Once you have the result of the statement, you can prove them easily. So the lemmas are the following. So actually there is one which is not obvious, but I will come to that, which that has been proved by Gormov. So any isotropic subspace is included in a Lagrange subspace. That's one. Two, any Lagrangian subspace is of half dimension. So, but this I said, yes, so I don't need to say that. Okay, so two, any basis. So any basis for a Lagrange, so any basis of a Lagrangian subspace. So any basis of any kind, you take just any real basis of a Lagrangian subspace, can be extended to a base, to a symplectic basis of V. Okay, perfect. Now the definition is the following. Now it comes more some things that are more relevant to the talk, to the series of talk. So a complex structure. The complex structure on V2nr. So you take any real vector space of dimension 2n. So by definition a R linear isomorphism, J from V to itself, such that J square is equal to minus the identity. Okay, perfect. So of course this implies that J gives endows V with a complex structure given by if V is inside V to nr, and if lambda is a complex number, then by definition the action of this complex number on the vector V is simply lambda V is equal to lambda 1 V plus J of lambda 2 V. Okay, perfect. Now comes the more interesting part of this story. Okay, so now we say that J is adapted to, so J is adapted or compatible, let's say. Adapted or compatible. Maybe compatible. Is compatible with beta if one beta is the J invariant. So this means by definition that beta of J of V1, J of V2 is equal to beta of V1, V2, or R V1, V2. And 2, beta of V, J V is larger than 0 for all V which is different from 0. Okay, so this is the definition of, okay, so this is the definition of a complex structure on a vector space, on a real vector space, which is compatible to a non-degenerate bilinear form. Okay, so it has to satisfy exactly these two properties. And so a consequence of that is that So if you have this, then it implies that you can construct a scalar product, and the scalar product will be called G of J beta, and it's given by definition. By definition, it's up to a sign. I never remember. It depends on the conventions, but let's say that up to a sign. Let's use the following convention: beta of J of V JW. Okay, so if you take this as a definition, then it's very easy to see that this is a scalar product. Okay. Okay, so you use the fact that G squared is equal to -1, and the fact that beta is alternate, so anti-symmetric, to show that G is symmetric. Okay, and then you show that G is not only symmetric, but it is also non-degenerate using that condition. Okay, perfect. So, okay, so now it implies that you can define an Hermitian product. Okay, now recall that. Let me remind you that we had a real vector space here, but now we have endowed this real vector space with a complex structure, so it becomes a complex vector space, and as a complex vector space, it has an Hermitian product, which is by definition given by J of J beta of VW minus iota of B beta of VW. Okay, now so you see that any two of these structures determine the other two. Of this, and up this, determine the other two. That's a very important observation. It's very important to see that once J is fixed, then any two of these structures determine the other. Not any two. Any. You just need one. So any of these structures determines the other two. Okay. Alors, yes. So. Okay, so I think I'm going now to state the main theorem, just a moment. Okay, so so the main proposition is the following. Okay, so you take V beta given, and this is non-degenerate. So given on V. So now then the set of all compatible. So beta compatible complex structures on V is non-empty and contractible. Okay, so so this is absolutely fundamental. I mean, this is probably the most fundamental fact in symplectic topology. Unfortunately, I do not know any simple proof of this. It is just linear algebra, okay? But you have to work. I mean, yeah. So I will not have time to explain that, but to give the proof. But what I could do is to post the proof on a site. I could do two things: either to copy the proof and then to send this to you the next time, which is possible. Or the other possibility is that I write it in LaTeX and then I put it on the site of the conference. I mean. Okay, bon. Okay, so but this is completely fundamental. So this means that okay, maybe I will just okay. Let me just skip this for the moment. I will come back to this. So So now the definition is that simp of 2nr is by definition the set of all A in GL 2nr that preserve the fundamental class, the symplectic form, the non-degenerate symplectic form. And then, as an exercise, you can prove that GL of 2nr, what do I mean to say? No, oops. O of 2nr intersected with GL of NC is equal to simp of 2nr intersected with GL of 2n of NC, which is equal to UN. Okay, actually, it's not an exercise. It's trivial. You know, I will just explain that in a minute. I said that any structure here. So if J is given, any structure here determines the other. So this is a consequence of that statement. Okay, so now maybe I should just finish by saying on this linear algebra thing. Yes, the last thing about the linear algebra is that, which is the following proposition, is the following: is that the maximal compact subgroup of SP to NR is exactly UN. And moreover, the quotient of SP to NR with UN is exactly the space of compatible structures. Such that J is compatible, is beta compatible. Okay, so that's enough for linear algebra. So I think essentially everything that had to be said, maybe with Claude also. I don't know if Claude did exactly the same, or maybe it's something a bit different. Did you say so? You did not mention. Okay. You did not mention complex structure. Okay.
Last week there was lecture on complex structure, and your proposition was proved last week.
Okay. Wonderful. This proposition was proved last week. Okay, great. But who was here last week? Okay, most people was here. Okay, perfect. Okay, great. Okay, so I don't need to define. To prove that. Okay, now we have to talk about Moser argument. But this I think that Claude did. Okay, so this is everything that you need to know about linear algebra. And yes, of course, I will not go into details of this because you understand that very well. But once you have this, of course, once you have understood this, of course, this applies. So if you have a symplectic manifold M, then you have this tangent space. And on each fiber of that tangent space, you can. So M is, suppose that now M is defined what is the symplectic manifold. So it is a manifold such that at each point, if you look at the tangent vector space, you have such a beta form, which I will call omega in general, okay, which used to be called omega in general. I use beta because in this case, beta is linear, okay, on the vector space, whereas here omega varies with the point. So for each point x, you have a form omega x, and then you have the space G of omega x of R. So yes, maybe I should have said that this space, I will denote this by J of beta. Okay, so now you take G of omega x, and because this is a contractible space, then if you put this on each fiber, okay, obviously then you have a fibration okay, whose fiber at each point is a contractible, and then you can find sections. And the space of sections is itself, of course, contractible. Okay, so that's the main idea is the fact, or maybe I can explain that right now. So the main idea is that because the space of sections is contractible, then what you do is you look at properties of M with these complex structures. So you pick a complex structure, any one, which is compatible with omega, and then so it means that you pick a section of this, okay, a section of this space here, and then once you have picked that section, then you can compute any complex invariance that you wish. Okay, so the number of complex curves that pass through a given points or that cross homology cycles or whatever. And then you have to show that this number or this invariance, whatever this algebraic invariant that you got, you have to show that it is the same if you choose another section. Okay. But now, because each fibers are contractible, and because therefore the space of all sections is contractible, then you can always deform any choice of a complex structure, almost complex structure, G0. So you can always deform an almost complex structure 0 to any other one, G1. And when you have this deformation, then you have the space downstairs of all this compatible J structure. Over each one, you just look at the moduli space of the geolomorphic invariance that you want to look at. And then you just look at what happens when this space varies along a curve in the base space that joins J0 to J1. And the point is that, of course, because this space can always be connected, okay, you have always a deformation from one to the other, and not only a deformation one to the other, but the space is contractible, which is even you have much more flexibility. But because you can always do this, then you have a cobordism. You get a cobordism between any invariant, okay, counting any kind of geolomorphic curve to any other invariant counting any kind of other holomorphic curves when you start from J0 to J1. Okay, so this is the whole idea of Gromov work. Okay, the whole idea is this, and this is why this lemma, which is so just basic linear algebra, is so important. Okay, of course, there are many problems when you do this cobordism, because you see, if your cobordism is not compact, okay, then the point is in a cobordism which is not compact. The point is cobordant to the empty set. Okay, you start with a point, and then you just move your curve. You start with a point with a curve, and you just move the curve to infinity, and then you just have a cobordism between the point and the empty set. So in this case, of course, it gives you nothing. I mean, so in order to apply this philosophy, you need to show that the space of holomorphic invariants that you get is compact in some way. Okay, and this is exactly the idea of Gromov compactness theorem, which is at the base of the definition of Floer homology and quantum homology, okay, that I will discuss a bit later. Okay. Okay, now the Moser argument. So I think, Claude, you talk about that, is it? Okay. So I'll go fast. Just go fast since you have. So. Okay, so so you start with a manifold, which is symplectic, and which is a manifold, which is not necessarily compact. Okay, and then you start with this, and then with a variation of your symplectic form in the same cohomology class. So in the same cohomology class means that, saying that the cohomology class does not vary means exactly that the differential with respect to time of omega t is equal to of omega t is exact. So this is some differential of a one form. Okay, then so what we want to do is we wish to construct a diffeotopy. Actually, we have the word diffeotopy in French, but in English, it's always called an isotopy. So maybe I'll call this an isotopy. We wish to construct an isotopy psi t of M to itself, such that psi 0 is equal to the identity and psi t star of omega t is equal to omega 0. Okay, so you see the program. So we have an exact deformation of a symplectic form in a symplectic manifold. And what we wish to show is to show that, oops, there's an M missing here. We wish to show that up to diffeomorphism, the symplectic form is always the same. Okay, so up to diffeomorphism, the symplectic manifold remains the same. It's very important. First, it's very important to have the same cohomology class, because if the cohomology class is not constant, if you take, for example, and it's a very simple example. So, for example, an annulus or a sphere, and if you change the area, the cohomology class, then it means that you change, in this case, the area, and of course, then you cannot have, of course, you cannot find a diffeomorphism that pulls back the one form to the other. Okay, so the condition on the fact that the cohomology class stay the same is of course necessary. But now the theorem is that it is sufficient. And I wish to explain this quickly because I think Claude did that. So how do we do this? So how? So we have d psi t over dt is equal to so evaluated at psi t of x, or x is any point of the manifold, is equal to xt of psi t of x. Okay, so this is because, yes, it's not an any isotopy actually. What we wish to construct, I should have said that at the beginning. It's not any isotopy, it's an Hamiltonian diffeomorphism. Okay, because it is an Hamiltonian diffeomorphism, it will be generated by a sequence, not a sequence, but by one parameter family of vector fields that are generated by some Hamiltonian HT. Okay, so because we have this as an hypothesis, then we are looking for that. Okay, so that is, sorry, we have this, okay, by definition of psi t. And then, so now the fact that d over dt of omega t is equal to d sigma t, this implies that 0 is equal to d over dt of psi t star of omega t. Okay, which is by the Leibniz rule equal to d over dt of psi t star applied to omega t. Okay, so this is so we know that omega t varies in an exact way. So applying this, we see that the differential, of course, so we are looking for psi t that pulls back omega t to the same omega 0. Okay, to the same omega 0. So we are looking for something which, of course, which does not vary in time. So it is equal to 0. And then you just apply the Leibniz rules. Oops, there's a term missing. In the Leibniz rules, you have at least 2 terms. Okay. So I just forgot the second one. So the second one is psi. So you have to you first differentiate psi, and then you just differentiate omega. Okay, perfect. So this is equal to psi t star. Psi t star of the Lie derivative with respect to xt of omega t, which plus psi t star of d sigma t. Okay, and this is so now okay. So this is equal to psi times t of iota of xt d plus d of iota xt applied to omega t plus d sigma t. And this is equal to 0. Okay, you see here Okay, you see here this is I'm just using the fact that the Cartan. I mean, there are two words for that: either the Cartan identity or the identity of the calculus of variation. So that tells you that the Lie derivative with respect to some vector field is equal to iota d plus d iota. Okay, so that's simply the basic identity in differential geometry. And then so this is equal to 0, and then this means that this has to be equal to 0 because psi is a diffeomorphism. And then we get finally that yes. Okay, perfect. So we get that that d of iota xt omega t plus d of sigma t is equal to 0, which means that, so now we just take the 2d at the same time. So it means that d of sigma t plus iota xt omega t is equal to 0, which implies finally that that iota xt of omega t is equal to minus. So it does not imply, but it doesn't imply, of course, but it is sufficient. So that this is equal to minus sigma t. Okay, so we get it. So what we get is that what we have to choose, if you denote psi the diffeomorphism from Tx of m to Tx of m, just given by v goes to omega v dot. So this is we know that omega is non-degenerate, which means exactly that this is an isomorphism. So we have an isomorphism here, and then we use that isomorphism to deduce that it is enough to show that to choose psi of xt is equal to minus sigma t. Sorry, this means that we have this. Sorry, so we have this, and then this implies that we have this, and then it means that xt can be chosen as being as minus psi of sigma t. Okay, so that's it. So that's the end of the proof. So this proof shows that if we choose the vector field, so we start with sigma t, which is a one form, any one form, and then we just take the negative of that, and then we use this isomorphism to pass from a one form to a vector field. Then we get a vector field, and then it's enough to take that vector field as the generating set of vector fields for the Hamiltonian isotopy that we wish to have. Okay, so this is enough. Note that it's very important. I mean, it's important to see that this is sufficient. Okay, it's not necessary. So, of course, once you have one diffeomorphism, where is it? It was upstairs. But in any case, when you have one diffeomorphism, okay, sorry, that's there. So once you have one psi t, then you can pre-compose or post-compose psi t with any Hamiltonian diffeomorphism, and of course you get another solution. Okay, this is exactly why we have sufficient here and not necessary. Okay, because this is true up to the addition of a closed form, and closed forms correspond to symplectic diffeomorphism. Yes, sure. Wow, finally a question. Sure. Yeah, sure. Thank you. That, I was going to say that. I wanted to say that, but I was forgetting. Yes, exactly. So my manifold is not necessarily compact, okay, because I wish to work in full generality. But here, of course, it means that the proof works as soon as you can integrate the vector field. Okay. Thank you for that. Yes, because actually it will come. It will come very soon in the following statements. Okay, so okay, so now the main proposition is the following, and here your remark will be essential. So the main proposition is that, oops, let Q. So this is really the main proposition about Moser argument. So let Q be any compact. So thank you for this. So any compact subset. Okay, just subset of a manifold, of a symplectic manifold. Okay, so of any not necessarily compact symplectic manifold. Then let omega 0 and omega 1 be two closed forms. Two forms, sorry. Two forms, yeah, on a neighborhood of Q. Let's suppose that. Actually, we have to suppose that. Let's suppose that omega 0 on Q is equal to omega 1 on Q for all Q. Okay, so here now I mean really the omega 0 is equal to omega 1 in the ambient tangent space. Okay, so what I really mean here is that you have Q here, you have Q here, and then you need that on the ambient tangent space omega 0 of Q be equal to omega 1 of Q. Okay, so on this ambient tangent space, not only on the restriction. Not only on the restriction to Q. In any case, Q has not necessarily any tangent space because it's any subset, compact subset. Okay, so now the conclusion is that there is a diffeomorphism that sends W0 to W1. Okay, so yes, let me see. And so. And that, of course, we need non-degeneracy, of course. So these are just any two forms, close to forms, but we need that they be symplectic near Q. So and that they be non-degenerate near Q in any small neighborhood of Q. Okay, then the conclusion is that there exists a neighborhood of, let's say, N0 of Q, such that and a diffeomorphism. Let's call it psi from Q, from N0 to N1. Okay, which is the identity on Q, and is such that psi star of omega 1 is equal to omega 0. Okay, so this is the main. This is exactly the Moser argument in its most general form. I'm sorry? N1 is just the image. Because it is the identity on Q. Yes, and a diffeo. So, of course, this is the image of a neighborhood of Q. So, this necessarily is the neighborhood of Q also. Okay, so, there exists two, if you wish, there exist two neighborhoods. N0 and N1 of Q. Such that. Okay, now let's see the consequences of that. Okay, so the consequence. So I will not prove that because it is one. So this is exactly a consequence. So I don't want to prove that, and I don't have time in any case to prove this, neither any of the consequences. But really, it's easy. If you have the Moser argument in mind, it's really easy to prove that. That's it. It's not difficult. So so the corollaries of this. So there are several corollaries. Of course, the first one is the Darboux theorem. Okay, which that you know. So for any x in any manifold, symplectic manifold, there exists a neighborhood n and a symplectic diffeomorphism. Diffeomorphism psi of n to the ball of radius r of 0 with a standard metric. Okay, so this is the first one. Okay, so for any manifold, for any point, there always exists a neighborhood n sufficiently small of that point of x and a symplectic diffeomorphism that relates this neighborhood to the standard ball of R2n. So this is the standard ball of R2n. This is a manifold of dimension 2n, and which is such that it is symplectic, so it pulls back omega standard to omega. So that's the first one, and then there are. Okay, so this is the first one. The second one is that if you take Q as a symplectic submanifold, okay, alors then the theorem is the following. So if you let Wi be included in mi, omega I, and so for I is equal to 1 and 2. So let's simply choose two symplectic manifolds and two symplectic submanifolds of the same dimension. Yes, closed, let's say. Huh? I need that also. Closed symplectic submanifold. And then so assume that. So assume that there exists a diffeomorphism. A symplectic diffeomorphism. I'm sorry, my notes are in French, so sometimes I put the adjectives before and not after. So assume that there exists a symplectic diffeomorphism, phi, let's say, from W to W1 to W2, and that phi star of omega restricted to W2. So that is W up W2. Omega 2 is equal to omega 1 restricted to omega 1. So then, so now this is just, oh yes, okay, it will be clear in just in a moment. What I mean will be clear in a moment. Okay, so assume that what letter did I show? It shows W phi. Okay, so assume that phi lifts. So in a way that we have Tx of m m1 to W1. Phi to Tx of m2 W2 over W1 by phi over W2. Okay, so we just have a symplectic diffeomorphism between omega 1 and omega 2. So as manifolds, it is not phi is not supposed to preserve the ambient the symplectic form of the ambient space here, but it has to do it. We need that it preserves the structure of the ambient space. So if we have this, then the conclusion is that then it implies that phi can be extended to a neighborhood. So it can be extended. Okay, to the neighborhood of W1 as a symplectic diffeomorphism. Diffeomorphism of n W1 omega 1 as a symplectic of 2 and W2 omega 2. Okay, so that's the theorem. So it means that if you have two symplectic submanifolds, then if they are isomorphic up to diffeomorphic up to in the same if they are diffeomorphic as a symplectic submanifold, then this symplectic homomorphism can be extended to some neighborhood of the symplectic submanifold. So it means that it means exactly the following. If you have two, it means that a symplectic submanifold determines its symplectic form near itself. Okay, so if you have a symplectic submanifold inside a big manifold, then if you know the symplectic submanifold, you don't even need to know the form in the ambient space. You don't need that. You just need to know the form on each tangent space. So if you know that for a given symplectic manifold, then it completely characterizes a neighborhood up to symplectic homomorphism of that submanifold. Okay, so this is a direct consequence of the Moser argument. And then the last one is for Lagrange submanifold. I'm sure that Claude explained that. So what can be the can you guess what is it? Well, of course you can guess because Claude explained that. But if you if you don't remember the talk by Claude, so how could you guess what is the statement for Lagrange submanifolds? Okay, because on the Lagrange submanifold you have nothing. I mean, because the symplectic form vanishes completely. So if we apply the same argument as here, we don't need to assume that there is any symplectic diffeomorphism here, and we don't need to assume that it extends here anymore. So we will have a very strong theorem. I mean, the strongest possible theorem actually that is going to tell you that if two Lagrange submanifolds are just diffeomorphic, then their neighborhoods are completely determined. Okay, so this is the next and probably last theorem. So not exactly the last, but yes, I wanted to talk about holomorphic functions and okay, I will not have time to finish exactly but I'm close to. I'm not so far from what I wanted to explain. So everything that is related to holomorphic functions and generomorphic curves and so on will be postponed to the next talk tomorrow, I think. But I just wish to finish these applications. It's very short. I will do this in 2 minutes. So now the third one is exactly what I explained. So the theorem is following. Suppose that Li is equal to Mi. So I is equal to 1, 2, and with Li Lagrangian enclosed in any not necessarily closed symplectic manifolds. So if L1 is diffeomorphic to L2, then there exists a diffeomorphism which is symplectic phi from some neighborhood of L1 to some neighborhood of L2. Okay, so this is the Weinstein theorem. Okay, one of the main applications of the Weinstein theorem, and then I will finish with this, is the application to generating functions. Okay, so this is very amusing. What happens here is the following. So let me just set this as a theorem. This is my last theorem. It will take just 3 minutes. So the theorem is the following. So suppose that you have a symplectic manifold. And then there exists an identification. So between a C1 small neighborhood of the identity of the graph, I would say. Yes, okay, of the graph of the identity. Okay, so you take m omega and you cross it with m minus omega. Then the fact that you have reversed the sign here does not change the fact that it is a symplectic manifold. And see if you have two symplectic manifolds, then the product is a symplectic manifold. So you look at this, and now you look at the diagonal inside this. And the diagonal is the graph. So this is the graph of the identity. And then now by the last theorem, by Weinstein's theorem, we know that. So the first observation is that this is Lagrangian. This is easy because this is omega and this is minus omega, so it cancels. Okay, so the form, if you restrict the form omega plus or times minus omega to the diagonal, then of course it will be 0. So this is a Lagrangian manifold. Now you have a Lagrangian manifold, and you have this neighborhood inside this product. And now you are interested in looking at what this could look like in a standard way, because we have this Weinstein theorem that tells us that any Lagrangian manifold is the neighborhood of any Lagrangian manifold is diffeomorphic, symplectically diffeomorphic to the neighborhood of any other. So now we just look for a standard representative of that diagonal, and so of course the diagonal is diffeomorphic to M by the projection, any projection that we like. So here is M times M. So this is M omega, and this is now M minus omega. Now you have the diagonal here. And of course this, by projection on either factor, let's see this one, is diffeomorphic to M, of course. So now we have another model for this, which is just a cotangent. I've not talked about that, but I'll just describe this very quickly. So the cotangent of any manifold is a symplectic manifold with the form omega, which is equal to d sigma, d lambda, and d lambda in lambda is simply, so this is M, and this is T star M. So now now this is simply the differential of lambda, and lambda is the canonical one form. That is, it's the only one form which is defined canonically, which is the following one. Here you look at the fiber. Because you have a fiber, it means that here you have the point x. Because you're on a fiber, it means that this point here is some p. So it's a cotangent vector by definition at the point x. And now if you have a vector here, what is this one? So what is this one form? This one form assigns to any vector like this the number that you get by projecting first this vector downstairs. And then once it is projected downstairs, then it belongs to the tangent space. And then you just apply p to that tangent vector. Okay, so lambda is by definition. Okay, lambda of any vector. So this is, let's call it v. So a V at the point X is by definition simply you have the projection here, pi. So you take P pi star of Vx, then you get a vector here, and then you apply pi x to that vector. Okay, so that's the definition. Okay, so this is a symplectic manifold, and it is obvious by definition. And it is a non-compact symplectic manifold. This is why it was so important in my talk to have all these Moser arguments for open manifolds, because I need open manifolds. And then so now it's very clear that the zero section is a Lagrange submanifold. This is obvious, okay, because the form lambda vanishes, so a fortiori the differential will also vanish. Okay, so we know that this is a Lagrange submanifold, and therefore we know this is Zm, and then by Weinstein's theorem we know that there is a relation between there is a symplectic diffeomorphism between some neighborhood of lambda inside m times m and some neighborhood here. Okay, and now it's a very easy exercise. Okay, it's a very easy exercise to show that. Okay, so if you have a graph, so now here it's the Lagrange. So there are probably. I will finish in 1 minute. So there are maybe two exercises. So the first one is simply to see that if something is C0 close to the diagonal, then it has, and if it is Lagrangian, then it is a symplectic diffeomorphism. Okay, so this is the first exercise. So if let's call it L, if L is the graph of a diffeomorphism of M to M, and is C1 close to the identity. So what I need is simply that it projects well, actually. C1 is, I could perfectly relax that C1 hypothesis, but doesn't matter too much. So which is C1 close to delta, to the identity, to the graph of the identity. Then it is Lagrangian if and only if it is a symplectic diffeomorphism. Okay, that's clear. Okay, now we could look at the question whether or not it is Hamiltonian, which is a much more interesting question. Okay, so I'll just leave to you this premise for reflection. But this is related to the theory of flux, the flux theory, which is not so easy actually. It's not. Okay, so don't panic if you do not solve that question easily. Okay, so this is a very simple exercise, and now we know that on the other side we know that we have exactly the same. So this is exercise 1, and I'm sorry I will finish very soon. So the exercise 2 is that if you have the graph which is C1 close to the zero section here, then it is a Lagrange submanifold inside the symplectic manifold exactly when it is the graph of a closed one form. Okay, so exercise 2. So if L is a graph of a one form, okay, so if it is any section that projects well on M, then it is Lagrangian if and only if it is a graph of a closed one form. So if and only if it is closed. Okay, now you just use Weinstein theorem, and then you can go from one to the other. And it tells you that the C1, so the C1, locally at a C1 level, that is up to a C1, in a C1 small neighborhood of each side, on each side, the graph, the symplectic diffeomorphism here correspond exactly, the symplectic diffeomorphism here correspond exactly to the closed one form here. Okay, once again, the symplectic diffeomorphism here correspond exactly to the closed one form. So it means that, so here, it's a bit surprising because this is a graph of any Hamiltonian diffeomorphism, not necessarily some diffeomorphism which is generated by an autonomous Hamiltonian. Because when it is autonomous, then we have H that generates the diffeomorphism, and then we can take DH, which is a one form. And then, of course, when it is autonomous, an Hamiltonian diffeomorphism which is autonomous corresponds to a unique, up to one form, closed one form. Okay, so if you look at things in this perspective, then you see that it is only, you could expect that it is only for autonomous Hamiltonians that you would have this correspondence between symplectic diffeomorphism and or Hamiltonian diffeomorphism and closed one form. But actually, this theorem of Einstein and this argument shows that it's much. If you look at things in this way, then any Hamiltonian diffeomorphism, which is small enough, okay, even the ones that are not autonomous, corresponds to the graph of a single closed one form. So this is why it is so powerful. And this idea and the idea of generating functions have been exploited and worked very well in the French school, and Claude is one of the best representatives of that effort to work on generating functions, and it has produced, I would say, many successes. Okay, I'm sorry, I'm a bit late.